Good day, I am Rainier Ginto, ID 123, and I will be teaching Foundational Math or FNDMATH Long Quiz 3. Basically, Long Quiz 3 revolves around trigonometry, so topics such as angles, angles of depression, elevation, and especially the trigonometric functions and trigonometric identities will be covered in this video. Okay, so first of all, let us talk about angles. Trigonometry is basically the mathematics that deals with triangles, and one of the most prominent features of a triangle are its angles. So we're going to talk about that. Angles are formed when two sides intersect. One is called the initial side, and the other one is called the terminal side. The initial side is usually the point of reference that we use when dealing with trigonometry. Their point of intersection is called the vertex, but those are like not much of our concern. Our concern is the measurement formed by such an intersection. This is the angle, and it is usually denoted by theta. Angles can be expressed in two forms. An angle can be expressed in radians and degrees. So what are these radians and degrees? Degrees is the division of a full circle into 360 parts. So each circle consists of 360 degrees. While for radians, it is the measure such that the arc, this semicircular arc, formed by such an angle or one angle of radian is equal to its radius. That's what a radian is. And each circle has 2 pi radians, or usually denoted for shorter as 2 pi rad. Now, both of these are usually used when denoting angles. And it's like a lot of people make mistakes when they thought that the angles given were in radians, or they thought that the angles given were in degrees. So let's talk about conversion between the two. Now, to convert from radians to degrees and vice versa, we need to use conversion factors. When converting from radians to degrees or rad to degrees, our conversion factor is 180 degrees over pi. Well, when we're doing vice versa or degrees to radians, our conversion factor is pi over 180 degrees. So let's do some examples. If I want to convert 60 degrees to radians, my solution would be as follows. 60 degrees times pi over 180 degrees. That would give me 60 pi over 180. However, we can actually simplify it. We know that both 60 and 180 are divisible by 60. So 60 divided by 60 equals to 1. So we can write pi. Then 180 divided by 60 equals to 3. Then here 3. So 60 degrees is basically equal to pi over 3 rad. How about the vice versa version, or from rad to degrees? Let's convert pi over 2 rad into degrees. So our solution would be pi over 2 times 180 degrees over pi. And this would give us 180 pi over 2 pi. And of course, there's a degrees too. However, we can cancel out pi over here. And 180 divided by 2 is equal to 90 degrees. So that means that pi over 2 is equal to 90 degrees. Moving on, let us now discuss quadrants. We've already learned about the quadrants in Cartesian plane. This is the first quadrant, the second quadrant, and the third quadrant. And this is the fourth quadrant. However, we usually use the Cartesian plane when plotting trigonometric functions, and it helps a lot in trigonometry. So the standard position of in trigonometry when we are plotting in the Cartesian plane is this. We usually align it with the unit circle, and our initial side is always lying on the positive x-axis. Then the side that moves is the terminal side, like this. And from here, different angles actually produce different terminal sides lying on different parts of the Cartesian plane, and they also lie on different quadrants. For example, this side is going to be 30 degrees, and it lies, of course, on the first quadrant. How about 270 degrees? Of course, this is 270 degrees, and it lies exactly on the y-axis, on the negative y-axis. 210 degrees, well, we know that up here would be 90 degrees, another 90 degrees over here, then that would make 180 degrees na. Then we add another 30 degrees, that makes this whole angle equal to 270 degrees. Then also we can do maybe 150 degrees. To make 150 degrees, well, we know that this is already 90 degrees, then this is 180. However, 150 is between 90 and 180. So let's count. This is 30, 45, 60. 60 plus 90 is 150 degrees. So that this makes it 150 degrees. Moving on, let us now talk about coterminal angles. Coterminal angles, by definition, are angles sharing the same terminal side. Basically, as shown in the figure over here, like this, 45 degrees, its terminal side is this black line. The same with negative 315 degrees. The thing about this is, when we are studying angles, we usually do counterclockwise direction. However, we could also do clockwise direction, and it turns into negative like this, negative 315 degrees. Then, what if we do full 160 degrees before making a 45 degrees? Here, we already made the 360, then another 45 degrees. We produce a terminal side that is also equal to the terminal side of both 45 degrees and 315 degrees. All of these three angles are what we call coterminal angles. Now, the thing about them is the difference between two coterminal angles is always a multiple of 2 pi rad or a multiple of 360 degrees. Let's take a look. For example, what's the difference between 45 degrees and negative 315 degrees? 45 degrees minus negative 315 degrees is equal to 360 degrees, which is a multiple of 360 degrees. And how about 405 degrees and negative 315 degrees? That would equate us to 720 degrees, which is also a multiple of 360 degrees. If we're going to look for coterminal angles using degrees, we need to find a multiple of 360 degrees. However, if we are in rad or radians, we need to find a difference of 2 pi rad. So how about let's get a problem here from syntax. So which of the following angles is not coterminal with 15 degrees? Now, in solving this, notice that some of the choices are not in degrees. So let us first convert 50 degrees into radians. So in converting degrees to rad, we use a conversion factor of pi over 180 degrees. So that's what we're going to do. So now we have 15 degrees times pi over 180 degrees. Now this gives us 15 pi rad over 180. However, we can notice that we can actually simplify this. Notice that both 15 and 180 are divisible by 15 itself. So let's do that and divide 15 and 180 by their least common multiple, which is 15. So 15 divided by 15 gives us 1, and we can just write pi over here. Then 180 divided by 15 gives us 12. So that means that 15 degrees is equal to pi over 12 rad. From here, we can now solve for which one of these are not coterminal with 15 degrees. Let's start with 105 degrees. 105 degrees minus 15 degrees is equal to 90 degrees. However, for two angles to be coterminal with each other, their difference must equal to 360 degrees or 2 pi rad. That means that 105 and 15 degrees are not coterminal with each other because they have a difference of 90 degrees, which is not a multiple of 360 degrees. So let's check if the others are also coterminal with 15 degrees or not. This one's in rad, so let's do 2 pi over 12 minus pi over 12 gives us 24 pi over 12, which gives us 2 pi, which gives us good. It's good. How about the remaining two? Let's do negative 23 pi over 12. This one's good. Negative 23 pi over 12 minus pi over 12 equals negative 24 pi over 12, which can be simplified into negative 2 pi, which is also good because it's a multiple of 2 pi. How about negative 705 degrees? So negative 705 degrees, this one's in degrees, so we're going to use 15 degrees. Minus 15 degrees is equal to negative 720 degrees. And notice that negative 720 degrees is also a multiple of 360 degrees. So yeah, it's good. It's also coterminal. That means that our answer for this question, since it is looking for the angle that is not coterminal with 15 degrees, that would give us this, letter A, 105 degrees. Okay, so let us now talk about the most common or most prominent features of trigonometry, the trigonometric functions. So basically, we usually know the three basic trigonometric functions, which are sine, cosine, and tangent. But what exactly do they mean? Well, first, we've tackled about angles, and we could define these three functions as a function related to angles. They are derived with respect to angles. However, in the context of right triangles, they could also be derived using the lengths or measurements of the sides. So as shown in the figure, if we have this as our angle theta, we could label our right triangle as follows. The one farthest from the angle is the opposite, the longest side is the hypotenuse, and the side that is shorter but just adjacent to the angle is adjacent. And from here, we can actually derive the ways of getting the values of the trigonometric functions, sine, cosine, and tan. We usually hear it in this form, the SOHCAHTOA, and it basically means sine is equal to opposite over hypotenuse, cosine is equal to adjacent over hypotenuse, tangent is equal to opposite over adjacent, which is basically it. That's it. However, we could notice that this part for tangent, it could be simplified into this because we know that opposite is also equal to sine theta times h. And we also know that that's from here. We derived it from here. And we also know that adjacent is equal to cosine theta times h. We derived it from this one, from the definition of the cosine function in the context of a right triangle under SOHCAHTOA. So if we divide this to O and A, we can cancel out h. And that leaves us with sine over cosine. And that's why we also have this identity. Tangent theta is equal to sine theta over cosine theta. Sorry about that. So let's try applying that into an example. So for example, we have a right triangle with measures of 5, 12, and 13. And this is our theta. Its opposite is 5, its adjacent is 12, and its hypotenuse is 13. So what is sine theta in this context? So in this example, sine theta would be opposite over hypotenuse, which gives us 5 over 13. Cosine theta would be adjacent over hypotenuse, which gives us 12 over 13. And of course, tangent theta would give us opposite over adjacent, giving us 5 over 12. And that's about it. And also notice that here, if you divide 5 over 13 by 12 over 13, that gives us 5 over 12 as well. Now, we've already shown or tackled the trigonometric function in a right triangle diagram like this. But what if it's in a unit circle? As I've said earlier, we usually use the unit circle when we are using trigonometry because it helps a lot, since it kind of gives the values of these trigonometric functions. When you're plotting or using the unit circle in the context of trigonometry, it usually goes like this. For example, you have a point here. This is a point that lies on the unit circle. Its x-coordinate is basically cosine theta, wherein the angle theta is over here. And its y-coordinate is basically sine theta. So that's why the unit circle is usually used in trigonometry. So this helps a lot because if you just move this terminal side around, it would give you all the values of the sine theta and the cosine theta now. However, it is still quite hard, especially if our point is not on the unit circle. However, when we have a point that is not in the unit circle, we can still look for its cosine and sine theta. Of course, we can use the approach given above. However, there is also another method. Here it is. We can use this. We can denote as cosine theta equals x over r and sine theta equals y over r, wherein x is the x coordinate of this point and y is the y-coordinate of the point. And r is the distance of the point from the origin. How do we get the value of r? It's basically just Pythagorean theorem. X squared plus y squared equals r squared. That's basically it. So how about, what if we have, for example, a point that is 0.34 and we want to solve for its sine, cosine, and tangent. So 1, 2, 3, yeah, like this. Well, we know that it is not on the unit circle, so we have to calculate for r, or the distance of the point from the origin. That gives us r equals square root of x squared plus y squared. I got this because I used square root on both sides. Square root of r squared equals r, and the square root of the sum of x squared and y squared. This gives us 3 squared plus 4 squared is equal to square root of 9 plus 16, square root of 25, which is equal to 5. We can now use this to solve for the sine, cosine, and of course the tangent. The sine is equal to y over r. Our y is equal to 4 from this point, because it should be the y coordinate. 4 over 5. And cosine theta is x over y. Our x is equal to 3 from here, 3 over 5. And if you divide this, you would notice that the tangent is equal to 4 over 3, because we just divide 4/5 over 3/5. You can subdivide this into 4/3. So that's it. Okay, so now how about we try solving this problem? Well, it asks us to find the value of cosine theta, given that cosine theta is basically the connection of a point from the origin towards a point P at 4, -5. So let's plot it. So it's not a straight line. Let's just pretend it's a straight line. And yeah, let's plot first where P is at. So 1, 2, 3, 4. And 1, 2, 3, 4, 5. That makes it -5. So -5 and 4, it's over here. Here is P. Let's label it as P. Okay, now the problem asks us to find its cosine. And from above, let's take a look. Cosine of a non-unit circle is its x-coordinate divided by its distance from the radius. So we still don't know what its distance from the radius is, so let's solve for it. R equals square root of x squared plus y squared. I'm just using the much more direct version of r squared equals x squared plus y squared, which I explained over here. So yeah, and we can substitute because our point is 4. Wait, I'll write it here. Our point P is 4, -5. So basically, this is x and this is y. Square root of 4 squared plus -5 squared gives us square root of 16 plus 25 equals the square root of 41. That means this r, or the distance of the point P from the radius, the point P towards the origin, is equal to square root of 41. So we need to look for its x-coordinate. And we already know its x-coordinate, which is 4. So that means that cosine theta, which we noted as x over r, could be solved by doing this. 4 divided by the square root of 41. And that's our answer here. It's letter D. Square the cosine theta is equal to 4 divided by the square root of 41. Okay, so now let's talk about reciprocal functions, or basically more functions, more trigonometric functions, which are in relation to the 3 most basic trigonometric functions. Basically, it means that cosecant theta is the reciprocal of sine theta, and secant theta is the reciprocal of cosine theta, and cotangent theta is the reciprocal of tangent theta. That's about it. So let's try solving a problem. In which quadrant is theta located, given that secant theta is less than 0 and sine theta is greater than 0? Well, so now let's try solving this problem here. Well, we talked about a while ago that sine theta corresponds to the y-coordinate of a point. It's in the Cartesian plane, yeah. So that means that from here alone, we can say that the point or the theta that we're looking for is easily only between quadrant 1 and quadrant 2. Cannot be in quadrant 3 or quadrant 4 because that would mean that sine theta must be less than 0 if they were in here. So it's either of 2. Now let's get our next clue. Our next clue states that secant theta is greater than 0. And secant theta, let us note that secant theta is equal to 1 over cosine theta, which is less than 0, less than 0. That means that cosine theta is also less than 0. Because if this was positive, if cosine theta was positive, then the answer would be positive because positive is positive 1. Positive divided by positive gives us positive. However, in order for it to be negative, cosine theta needs to be negative or less than 0. So that means the x-coordinate of what we are looking for is less than 0. So from here, we can say that it's not in here. So it's not quadrant 1. So our remaining answer is quadrant 2. And therefore, the answer is here is theta theta is in quadrant 2. Thank you so much for watching. You may also avail syntax tutorials by scanning the QR code flashed on your screens. Once again, this is Rainier Ginto from Syntax, paving your way to excellence.